Yeah. Nick, gonna go geology.
The board is
Geology is a
green.
go.
Go.
All right. Dave, gonna go amateur astronomy.
Go.
All right. Pam, gonna go on events
Go.
and astronomy. All right. Perfect. I guess we have
Go.
liftoff. Yeah. Do we do this? Is this the new thing that we do? That feels ridiculous.
It does seem a little
love it.
silly.
We used to just ramble on into the start. And oh, by the way, we've
Yeah.
started now. It's like, oh,
Yeah.
wow. Okay.
Yeah, exactly. At some
You know,
point.
that kind of works
Right.
too.
Yeah.
Yeah, it's at a certain
There's a
point.
whole literary term for that in Meteor A.
Yeah.
Oh, sorry, what?
I have heard that before.
In the middle of things.
Oh,
Yeah.
okay. Okay.
Oh.
That's hilarious.
Apparently it's cooler if you say it in Latin.
Interesting. How's that all going? So are you guys, I mean, I guess we're gonna get into the storm story, but it's starting to just suck up more and more of the resources of everything we're working on at this point. It's kind of amazing. Like you could tell people are starting to sense that something very important may or may not happen. And I'm getting,
That's good then.
Yeah.
it better be.
Yeah. For 1 a.m, it better be.
Yeah. Yeah, I think I'm well positioned. Well, it'll be still a little light.
Yeah.
me.
You guys are still going to have it's going to be like 9 or 10. It's already getting for the equinox. So yeah, you guys are like sunset probably is like what, 10 o'clock there, 9:30 now?
Yeah, 9:30. We're, we're
Which
still
day
like,
is this happening again?
Monday night, 30th into Tuesday morning, 31st.
yeah.
So
I'll
it's-
have just
for
gotten back to Phoenix.
East Coast here, it's going to be about 1 a.m. is the key time. So I'll probably just stay up late.
Yeah, and it's funny because I've been getting a lot of people in Europe and stuff, and they're going, really, like 8
Well, they
a.m. for us.
It's worth watching a bit early. It could arrive, it could kick into gear a bit early. That's all.
Hours early.
Yeah, yeah.
I mean, the Perseids, it takes sometimes like a day and a half, 2 days before, and a day and a couple, afterwards.
Yeah,
You get nice, long, slow.
some showers
rise.
have broad. Yeah, some like the quaternids in January are very. I've never really seen a good showing of them because they're powerful, but they're very quick. They're only an hour or two their window usually. Some have very very narrow peaks. So
Yeah.
I was going to joke that I wanted to see a meteor shower that was just condensed down to half an hour, like all of it in this nice little short period.
So that's what this might be.
well, I saw the 98 Leonids, so I know what they can be, and that was pretty amazing. That's the most amazing one I've seen.
Yeah.
Was it a
all right?
meteor
let's,
shower or meteor
let's
storm?
Get started. Storm.
It was a storm. Usually I hear 1,000 per hour is a storm cutoff. So I would say the Leonids in 98 were reaching that around sunrise.
Yeah. All right, I'm going to start. Hello and welcome to the Weekly Space Hangout for Wednesday, May 25th, 2022. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about, of course, the Tau Herculid meteor storm. We're going to talk about Starliner. We're going to talk about other events in astronomy coming up, NASA's objectives for the Moon to Mars exploration, and NASA's reference mission for the first human exploration of Mars. Joining me this week, we've got Dave Dickinson. Hey, Dave.
Hey, I'm down to my one ordinary scope now. Both my smart scopes are gone.
Oh,
so
no.
I had in the back. So
Oh, that's too bad.
But I like my little dumb scope. So.
But you do miss your smart scopes.
Oh yeah, they are addictive, definitely.
Yeah, yeah. We got Pam Hoffman. Hey, Pam.
Hey, Fraser. Good to
And
be here.
we've got Dr. Nick Castle. Hey, Nick.
Hey, how are you guys doing?
Good. All right. Before
Awesome.
we get into this week's news, and our interview, I want to give a huge shout out and thanks to our good friends of the Weekly Space Hangout crew. They're our friends, our fans. They call all the shots. They tell us what to do. So if you want to join this elite community, go to wshcrew.space and you can sign up. And they have a page. I guess this is CosmoQuest Patreon. So if you want to contribute to what we do, you can go to patreon.com/CosmoQuestX. All right, let's get into this week's special guest, Dr. Lia Medeiros. Welcome to the show.
Hello, Hello, thank you so much for having me. I'm very excited to chat with all of you.
So the question I always like to ask people, who are you? What do you do?
Good question. So I am a National Science Foundation Astronomy and Astrophysics Postdoctoral Fellow at the Institute for Advanced Study, which is in Princeton, but not associated with the university. They want to make sure I clarify that. And I have been a member of the Event Horizon Telescope Collaboration for about 7 years now. So pretty much since the very beginning of when I started doing research as a graduate student. And the last couple years, I've been leading the gravitational physics working group within the EHT. So there's a larger collaboration, and then the collaboration is also organized into smaller subgroups that each focus on different aspects of the larger project. And so when we published our 2019 image of M87, we didn't have a gravitational physics working group. And so I was one of the starting coordinators, and I've been serving as coordinator for that for almost 2.5 years now. And so the new result that we just saw just a couple weeks ago now, for the first image of Sagittarius A, we published 6 papers for that. And so I co-coordinated the 6th paper in the series, which is the paper that focuses on how we can use this beautiful image to actually test Einstein's theory of general relativity, and how we can use it to test fundamental physics in general.
Now, we've been enjoying the image of M87 for years now, and we've been quite excited to anticipate the image of Sagittarius A. And when we saw it, it's both not surprising, it's another donut, and yet surprising that it has very interesting and different structures than what we saw with M87. How did seeing this image finally come together? Did you have any kind of realizations or any deeper understandings about black holes as you even just saw this image?
So that's a very good question, but let me tell you a little bit more about it, kind of how this happened and how this was different from M87, because I do think that the experience for all of us was very different with M87 compared to Sagittarius A. So for M87, I was part of the team that made the images, and we were all in the same room, and we all pressed the button at the same time. And within seconds, we saw this beautiful image.
Right.
And we were all in shock and so excited. And honestly, myself and others, we thought that maybe it was a test that somebody else had given us, like data that was fake but was way too perfect. And we're like, no, this is too good to be true, because it was exactly what we expected. And it was so easy for us to actually get that result and get that image. Sagittarius A was absolutely not like that at all.
Yeah.
I can't tell you the moment that I, realized this. There was no specific one moment for me, because it's been a very long journey to get to this image and to get to a point where we really trust this image. So yes, thank you. I actually made this graphic, so love that you guys are showing that. And so they are similar, but they are also different. And in particular, what I want to emphasize here is that the fact that Sagittarius A has these 3 separate blobs, don't waste any time trying to interpret that. That could completely be an artifact. We don't think that that's necessary, right? And so they are different, but really they're more similar than different, I would say, especially, the parts of the images that we really believe and we really trust are the same for both, I would say. And so, what do we learn? So from the testing gravity point of view, we are at a vastly different mass scale. And so I always say that when you test a fundamental theory, it's really important to test it at different mass regimes, different regimes that are relevant for whatever theory you're testing. And so having a test in the strong field for a black hole of this mass, it is very exciting, and it is consistent with all of the predictions from Einstein's theory.
It's interesting when, after the Event Horizon Telescope had taken its first image, and then we got the announcement that there was going to be the big revelation, we were all expecting it to be the Sagittarius A image, and then it was the M87 image, and the question we as journalists were like, what happened to Sagittarius A? And the gist, the answer that I got from astronomers was, it's a very dynamic environment. The data is really tricky. M87, because it's so big, because it moves so slowly, it was easier to tease out this image and Sag A star is just going to take years for us to get to the bottom of this. What new techniques, methods did you have to come up with to be able to finalize on an image that you felt well represented the underlying data?
Yeah, so there were so many different techniques that have been developed, and I think that for me personally, the time that I really started believing it was when we had a fairly large number of different techniques that arrived at the same answer, right? And so one of these techniques, for example, has a model for variability, and so it essentially allows like an additional uncertainty in your image that accounts for the fact that there is an expected level of variability, so you don't expect your single image to fit your data perfectly, for example. There are other techniques that try to fit subsections of the data. And so, we have about 12 hours or so of data. And so instead of trying to fit the full 12 hours, you could try to fit 1-2 hours at a time and then have several images that you then average, for example. So there were several different attempts at how to deal with this. And it really did take a lot more of our time and effort to really get to a point where we felt confident enough to really publish this.
So now with 2 images of supermassive black holes at these widely different mass ranges, do you have some conclusions about black holes, do you think?
Yeah, so we have, so I'm going to be, this answer I'm going to focus on what's in the paper that I co-led. So in that paper, we look at a few different things. So first is what you see in the image is a ring. And we very, very carefully calibrate using a really large set of simulations that include simulations that are consistent with the predictions of general relativity, as well as simulations that are inconsistent with the predictions of general relativity. So we use a very large, broad data set to calibrate this measurement of this ring size. And a lot of different things go into that measurement, but our error bar that we arrive at is about 10%. This is significantly smaller than what we had for M87, and the main reason for that is that we know the mass and the distance to Sag A star so much better. It's really, really important and a really exciting part of Sag A star as compared to M87 is that we do know the mass and the distance incredibly well. And so that 10% error bound can then be used to constrain deviations away from the predictions of general relativity. And so the way that I like to explain this usually is that general relativity predicts a very specific black hole. It's called the Kerr black hole. It's named after somebody. And the point here is that what the EHT is doing is testing whether black holes in space are consistent with this very specific black hole that is predicted by general relativity. And so the size of the ring has to be a certain size that only depends on the mass and the distance. It has a very weak dependence on spin. And so by measuring that size, we can test whether or not our black hole in space is consistent with the black hole that is predicted by this theory. And in particular, we can also look at black holes that deviate from this specific black hole that is predicted by GR, and we can place constraints on those. And so that's one of the things that we do in this paper. But additionally, we also talk about whether or not this thing needs to have an event horizon. Right, so I feel like event horizons are one of the main things that most people know that black holes are supposed to have. But, and I think most of us expect that, yes, they do have an event horizon, but it's still good to be able to actually prove that, right? To be able to actually tell whether or not they do have an event horizon. And so we explored a few different possibilities. So one of them is, instead of an event horizon, this could be an object that has a surface that absorbs light that's shining on it, and then that light will heat it up, and because it's heated up, it will then emit, right? We can rule that out pretty conclusively. Or we looked at, instead, what if it's a surface that kind of acts like a mirror that just reflects light? A perfect mirror, we can also rule out. The other option is a naked singularity, and we can really constrain a couple examples of that, but we cannot rule out all naked singularities.
And with a naked singularity, you've got I guess it rotating so rapidly that the event horizon is revealing the singularity itself.
That is one example of a naked singularity.
Type. Okay.
Is a Kerr black hole that has a spin that's above 1, where 1 is what we consider maximal, because if you pass that, then it has these weird properties, like it becomes a naked singularity, for example. But there are other naked singularities as well.
It is interesting to me, though, that the kinds of objects that you're describing haven't been considered as theories for black holes for quite a while, and yet, I guess this is science. This is about definitively doing, making sure that this thing doesn't exist, and this is how you do it.
Exactly. That's a great way to put it. Yeah. So the approach that we took on this paper was definitely not to argue that the things that we're testing are the most well-motivated, or, the ones that we would expect, right? But the point here really is that even though there are reasons why we would expect that this object has an event horizon, and all of our understanding of black holes predicts an event horizon, the fact that we can actually use real observational evidence to actually prove it is still really, really exciting and really important.
Yeah, it's like still disproving hypotheses as you go, which is the fundamental. It's like the bedrock of science, and still, even at this level, coordinating the telescopes around the world and crunching on data for 5 years, you can go through that checklist and go, nope, 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 nope.
Exactly.
What theories remain? I mean, you've got a Kerr-style black hole. Are there some that still fit the data?
Great question. So a lot of my own research uses, actually, let me take a couple steps back here. So I want to make sure everybody understands what I'm about to say in the public. When I talk about a specific black hole, what I'm really talking about is the geometry. And that's really what general relativity cares about. And so there is this specific geometry that is the one that black holes should have if general relativity is correct, and also a couple other assumptions, which I can get into if people are interested. A lot of work, what I do is I look at what happens if you just treat this as geometry and add deviations to it. So you kind of think about it geometrically, and you have this Kerr black hole, but then you're going to change it slightly, and you're going to ask what happens. And it doesn't mean that I'm proving any specific modified gravity theory, but rather there's a lot of different ways that you can try to change the geometry, and you can rule parts of that out, right? And so 10% rules out a really big part of the parameter space, but there is still room within that 10% for deviations. And there isn't a super intuitive way for me to describe the different ways in which the geometry changes, because it is in 4 dimensions, and so it's a little counterintuitive, but there is still room for deviations, right? And for example, there are still ways that this could be a naked singularity, and it could be consistent with what we've seen, for example.
And so if you had higher resolution, let's say you added a bunch of space telescopes to the picture and made a much bigger interferometer, could you then come back and start to, I guess, maybe try to answer some more fundamental questions about, say, about the general theory of relativity, try and bridge gaps between quantum mechanics and relativity?
So the way that I like to describe this is that when I was first applying to graduate school, I wanted to use black holes in space to test fundamental physics, and that just wasn't a thing that humanity had done yet. That just wasn't possible yet. And during my PhD, we had the first ever detection of gravitational waves, and just a couple weeks after I defended my PhD, we had the first ever image of a black hole that was published. And so I think it's a really, really exciting time for the field. It's amazing that we're able to use these wonderful, amazing, crazy objects to test fundamental physics. But I really do think that this entire field is at the very beginning, and I think that there's a really, really exciting future ahead. And so, in particular, just to give you an example, so far, all we can do is use this ring size, right? And that's what I've been talking about, is that we're using the size of this ring to test. deviations from this curve prediction. But the shape is actually super important. The reason that we did not include the shape, actually, I can totally use this graphic. Yes, this is good. I will get to it in a second. So the reason that we don't include the shape in our analysis is that there's a lot of uncertainty in that shape because we had such limited baseline coverage, which just means we had a small number of telescopes. And so we've also observed in 2018, we observed again in 2021 and in 2022 as well, each time with additional telescopes. And so one of the things that I'm personally most excited about just in the next couple of years is that with additional telescopes, I think that we'll be able to really constrain the shape of this ring. And the shape of the ring is directly correlated to the quadrupole moment of the metric, which just means that it's correlated with something that's really important for us to test, because this thing called the no-hair theorem, one of the main assumptions of that is this quadrupole. And so if we could detect a deviation from what is predicted for the quadrupole moment, we could violate the no-hair theorem, which would be super important for the information paradox, for example, since the no-hair theorem is one of the assumptions of that. And so, it's all kind of a big web that if you kind of pick one of the threads, you kind of unravel a lot of different things. And so in this graphic, what this is showing you is how we actually calibrate this ring. And I think that this is really interesting. So the first one that's labeled black hole shadow shows a bunch of lines. And these lines are the trajectories of light as light is moving towards the black hole. All of the blue ones fall into the black hole and all of the red ones escape. This black hole shadow feature is defined by these blue photons, blue light rays that fall into the black hole. What I mean by that is that there is this geometrically defined feature that only depends on the shape of the black hole. And that's what's determining how the light moves through this curved space. And then when you actually go to the next step where you actually make an image of that black hole where you have matter swirling around it and that matter gets heated, then that's the middle image, which is showing you the result of a simulation that I ran. And then the final step is when you go from this perfect simulation image to what the EHT would actually observe, where you take into account the fact that we have a limited resolution, limited number of telescopes, so forth. And so our error bar, this 10%, includes both the difference between this essentially analytically defined feature and this bright ring of emission, theoretically, in our simulations, as well as the difference between the bright ring in the simulations and the bright ring in the actual image.
And so, with these additional observations, with the additional telescopes, that's going to give you, I guess, more photons, but not necessarily give you a larger baseline.
Good question. Okay, so it's not going to give us a larger baseline, but what's important isn't actually the number of photons. What's important is how much information we actually have about the image. So I don't want to get into too technical details here, but what you need, at least maybe need to understand, is that there is this mathematical equation that takes the data that we actually observe and makes it into an image, okay? And it's called the Fourier transform. It's super powerful. You actually use it all the time in your daily life. This is how all of signal processing depends on Fourier transform. Yep. But the idea here is that we observe, so each pair of telescopes observes one specific location that has a little bit of information about the image. And it's not really a pixel in the image. It's a pixel in this image after it was transformed with this weird mathematical equation. And you don't really need to fully understand the details of the mathematical equation to just know that there is, you go from the image and then math happens and then you get to something else, right? Right. That's the main point here. And so we observe, each pair of telescopes observes essentially one pixel in this Fourier transform image. And what we have when we have additional telescopes is that we can observe different locations. And so you get more information about the image. And what's really important is that for M87 in particular, for the image of M87, we essentially had information along two directions, which meant that we could really just probe what is, kind of two axes of our ring. but we couldn't have any more information about the shape of the ring than that. And so it's not that it's going to necessarily be higher resolution, but what is really exciting is that we will have much higher fidelity and much more confidence in the specific features of the image, and specifically more higher fidelity in the actual shape of this ring.
Right. And which is perfect to be able to analyze against these various theories. Are there any other targets? I mean, we're so lucky that M87 and Sag A star are roughly the same size on the sky, even though they're vastly different distances away from us. Is there a third that you could go after that's just within reach?
Also wonderful question. So we did get incredibly lucky that these two black holes worked so beautifully for what we wanted to do. We have observed other black holes as well, but they are much farther away. And so we don't get this pretty little donut shape that we've all grown to love. And so we can't do the same tests, but we can get essentially the highest resolution images possible for these other black holes that are more distant, and some of them are in very different regimes of accretion, which just means that these two black holes are eating very little, but these other black holes that are farther away are actually eating a lot more.
Right.
And so they can create these really powerful jet structures, and we can image those. And so we can learn a lot about those black holes and what causes these jets and how they're behaving and what that looks like at a finer scale, which again is super exciting and super interesting science, but it is different from what we can do with these two black holes.
Now, I get this question a lot from my viewers, and this is like, now that James Webb is coming online, will it be able to contribute? I mean, obviously it's not a radio telescope. It's, it doesn't have the resolution of the entire planet Earth, but it is infrared, and it will be able to see through the gas and dust to the heart of the Milky Way. Will it be able to help, sort of as a Nick geology type concept, but to give it sort of set and, give it its surroundings? Will you be able to use that for being able to sort of give an understanding? What's the term, Nick? You know what I'm talking about? Where geologists will look at the story of where the rock came from.
Yeah.
Context.
Context. There you go. Yeah.
Yeah. So it won't contribute to the image in particular, right? Like, we're not going to get a higher resolution image working with James Webb.
Yeah, of course.
For obvious reasons. But multi-wavelength observations are a really, really important part for us to understand the full picture. And there are already multiple ways in which multi-wavelength observations have been used in these results. And then, of course, it would be wonderful if Webb could add to that. So, for example, in what I've been talking about, when I was talking about ruling out a surface that absorbs incident light and then gets heated up and re-emits it, the way that we ruled that out, we needed two things. So there's essentially two free parameters in this model. One is the size of the emission region, and that we get from the EHT image. And that was the new part of this larger picture that we got from these new results. The other part is the amount of infrared radiation we receive. Because if it were to absorb and re-emit, it would be emitting the infrared, right? And so this super exciting result of we can rule out a surface that absorbs and re-emits, that already relies on infrared detections, right? And additionally, paper 5 in the series, which focuses on using a large set of simulations and constraining different parts of the parameter space for accretion physics, really trying to understand what goes on to this matter that's swirling around, getting hot, and falling into the black hole. That also used a lot of information from multi-wavelength studies.
Yeah. It's a fascinating time. Well, congratulations on the work so far and getting a chance to see this thing for real, which again, it's got to be as exciting to you as it is to us. Absolutely incredible.
Yeah. We've gotten very attached to our fuzzy donuts.
yeah, exactly.
Well, thank you so much for having me. I've really had a great time.
All right, and good luck with your future research. Whenever you let us know when you see the photon ring. Yeah,
we'll definitely let you know.
Okay, thank you so much. Take
Bye.
Care. All right, that was so cool. Sorry for running
Wow.
long, but that was so exciting. Okay, Dave,
That was
a
interesting.
ton of fun.
blow our
fascinating.
minds with the possible meteor storm.
The meteor storm that may be the meteor storm of the century, or nothing at all.
Or nothing at all.
This goes back to a particular comet that was found in 1939, and I'll say the full name one time, and then after that, it's a short period comet, so it's 73P Schwarzmann-Watchman 3, and herefore referred to as Comet 73P. This comet was discovered in 1939, and there was kind of some interest around it in the fact that it really kind of underperformed until 1995, when suddenly observers started reporting a 400-fold increase. And when they started looking at it with Hubble and various instruments, they found that the comet had indeed fractured and fell apart. It had undergone a brightening event, and a lot of that material got sprayed out along its orbit. Now, that's usually what we have for meteor showers, is we're intersecting these ancient streams and paths of meteors, like the Geminids is actually rock comet 32 Phaethon. The Perseids are Swift-Tuttle. That these streams happen to intersect the Earth's orbit. There's some interest, and we knew this earlier this year, that we may intersect this 1995 stream right when this comet underwent this ejection event. And there's 3 independent studies out there right now that show that we may have a pretty good encounter with this 1995 stream this coming Tuesday on Monday night, which Monday night for the 30th, the morning of the 31st. So the key time is right about half an hour on either side of about 1 a.m. Eastern time, which is 5 universal for you guys, around 9 to 10 Pacific time, which actually puts the radiant right above. It's interesting. This shower that's associated with Comet 73P is called the Tau Herculids, because in 1939, the first time this very week, usually most years, it's one of those really obscure showers that produces not much more than the background sporadic rate of 5 meteors per hour. You wouldn't even really notice it. It gets its name from the star Tau Herculis, which the radiant used to be near. Now the radiants evolve and move over time. So the radiant actually isn't in the constellation Hercules anymore, although it's in the adjacent constellation of Bootes. However, we can't call it the Bootids because there's already the June Bootids, so that would get a little. So there is some discussion out there, and you always have to preface it with saying, yes, they're the Tau Herculids, but they don't come from Hercules anymore. They actually
close
come
enough.
Pretty close. Yeah, Bootes is an adjacent constellation. And the radiant sits, if you can find Arcturus, which is the brightest star in the Herdsman, and you can find the handle of the Big Dipper, Alkaid, that final star, it's about a third of the way from Arcturus to the handle of the Big Dipper. Now, the radiance, of course, just where the meteors seem to be streaming from, the meteors will appear anywhere throughout the sky. But there are estimates that we might have a zenithal hourly rate. I've seen anywhere from 10-fold increase, which would put it on league with the Geminids, Perseids. If it's 100-fold, however, we're in meteor storm territory, which you're seeing one every few seconds. Now, I've seen the Leonids do this. In recent times, we always like to say that there haven't been any good naked eye comets since we went to digital astrophotography. Same with meteor storms, really. There were the Draconids, which were very briefly approached 800 per hour in 2012, but most people didn't see them. We haven't had a really good, the Leonids perform about every 33 years. Around 98 to 2000, where I saw them in Kuwait when I was in the Air Force. That was a very dark site out at Al Jaber Air Base, and we sat out and watched all night. And it was very impressive that we were seeing one every few seconds. And it was enough that there were bolides going off behind us, and we knew we weren't catching them because the whole desert floor was lighting up as we were seeing these. So I was fortunate we were at a very dark area at that time, and we saw. I would put that up there right along with the total solar eclipse in the Northern Lights, a really good Northern Light display, as some of the coolest things I've ever seen.
But I've heard estimates that are even higher.
Oh, yeah. And the Leonids in 1966 were like up toward 100,000 per hour, where, some of these storms can reach really amazing levels. The Leonids are notorious for that. some years, 1833, 1966, in the American Southwest, they saw it toward 100. They said they were seeing so much, they were getting that, the snowstorm, the Star Trek effect, like when the warp drive goes on and you're seeing the streams of stars go by you. They said you were literally getting this sense of the Earth's motion through space because there were so many meteors going by. So that had to be pretty incredible. The shower is interesting that the stream is approaching us from behind. Usually the Earth is going headlong into the meteor stream. This one, and this may, I always put this as a caveat, this may be one thing that might give this stream problems, is it's coming at the Earth from behind. So the meteors are going to have a relatively slow 17 kilometer per second velocity, which is slow for a meteor shower. The Leonids are about 72 kilometers per second. So 16 kilometers per second for this shower. So they have to do the upshoot of that is you'll see a lot of long, stately meteors instead of those really quick, zippy meteors that you see from the Leonids. But they also have to catch up to the Earth. So you need some good size, hefty particles to really ignite and get some really good fireballs going. But it's going to be worth going out there. I'm going to be out there at 1 a.m. I'll probably watch for half an hour. And if it looks like, and I'll look at, you guys where it's still daylight, watch Twitter. You'll probably see Twitter blowing up if it is meteor storm proportions. So.
And for people who are not well situated, like as you said, for me on the Pacific coast, it's 10 p.m. For you, it's 1 a.m. Europeans, it's like 5 a.m. for them.
Yeah. And I would start watching early when they're turned forward. It might arrive an hour or two early. That does happen. Activity may already be ramping up. So if you're in the UK or Europe and it's 2 a.m., if it's clear, I would go out and watch for 10 or 15 minutes.
I mean, we just don't know how much this trail has widened out over time, and then because of, as you said, its motion it's catching up with the Earth. I mean, it's possible that you could see it with many hours before and many hours after. Like, part of the excitement of this for the scientists is that we saw this breakup. Yeah. And now we'll be able to see the meteor shower that's associated with the breakup, and that'll tell us a ton of information about how these cometary trails will come apart, how they'll spread out over time,
how it was ejected during the 1995 event is really key. Whether it was ejected, the material was ejected forward or behind the comet, and how that stream evolved over the 27 years in between. And a lot of that is kind of unknown, but I think it's interesting that 3 separate studies looking at the model of the stream are kind of converging on meteor storm territory, which is kind of interesting. So it's watching.
Yep. All right. Very cool. Pam.
Yeah, and I like to talk about things that you can do, and that's sort of the top of my list today. Do we have even another May meteor shower? And I've been hearing SW3 for this Walkman.
Yeah. Some people shorten it as SW3.
Okay, great. So and that was just fabulous to have so much more information. I do have kind of a cool picture of it. From Earth Sky, as well as Space Magazine, space.com. Yeah, there it is. And so, I'll talk about some other things, like the planetary action is really still in the early morning. Some of the beautiful strings we've seen in the past are going to come back around. So that's kind of cool. I've got 2 cool activities to talk about, 2 globe at night projects, 13 conjunctions in the next month, but 7 are worth talking about. No eclipses. Sorry. So one of the things, where we go here? Okay, here we go. One of the things I wanted to mention was that you can still add your name to this Artemis program. We keep checking and it's still available. So add your name, they'll put it on a thumb drive and launch it around the moon. That should be pretty fun. Then we've got also the Space Prize. And I think they added something since I talked about it last time. Of course, this is going to launch in June. It's Space Prize Global. It's a worldwide contest to promote the advancement of women in STEAM, STEAM, that's science, technology, engineering, arts, and math. And they're specifically focusing on aerospace for this. They are opening this to anyone who's 15 to 18 years old, a young woman, anywhere in the world. So this will involve written, video, and creative submissions. The grand prize winners, there'll be 2, are going to receive about $250,000 worth of private astronaut experiences. And the thing that I think they added was this ride on the space perspective. And I know that's going to be pretty exciting when they actually get that going. Does anybody know kind of what their status is lately? I haven't really checked in.
I don't know what their status is, but space perspective, this is the balloon trip.
Right.
So it's going to go to 30 kilometers altitude. You will be able to see the curvature of the Earth. And what's different from Blue Origin and Virgin Galactic is that you'll be able to sit in this nice stately room with a comfortable seat, tasty beverage. There's a bathroom, there's snacks, and you're able to just float around for a few hours before you are returned to the ocean. So the thing will land in the Atlantic Ocean, and then it'll be recovered.
Yeah, none of this rocket launch stuff with your
no. Yeah, nice and civilized way to see the curvature of the Earth. I've said this is the space tourism that I'm most excited about right now.
Yeah, I'm good for like more room, a little bit claustrophobic here, but want to go out there anyway. Yeah. So next I want to tell you about Globe at Night, and this is pretty cool because they have projects about once a month. The next one is May 21st through May 30th. They last for 10 days, and in this case, if you're in the southern hemisphere, you want to look at crux. In the northern hemisphere, and Dave, I've always heard it called buutes. You want to look for buutes?
It's got the umlaut in there, so it's a little ambiguous for the pronunciation.
I just say booties.
Booties?
Yeah, some people just say booties.
Yeah, in the United States, that's something else.
Yeah.
And so the
My
next
favorite
one of
literature reference to it is Ada Boot.
Ada Boot.
Or Ada Boo.
Okay. June 19th through June 28th is the next one, and in the northern hemisphere, you're going to look for Hercules. The southern hemisphere, you're going to look for Scorpius. And each of these projects, like I said, lasts 10 days. The idea is to go out, take a picture of the objective for that night, and compare it to the things that they have. Oh, yeah, we got one more here. If you want to see the graphic of Crux and Buutes and Hercules and Scorpius, and take these pictures and compare them to what they have on the site. And I think this is a great way to contribute to a real citizen science project to really help make a difference out there. And so the various conjunctions I wanted to tell you about: May 26th, Venus and the Moon are in conjunction. May 28th, Jupiter and Mars are in conjunction. On the 29th, Mercury and the Moon. Like I said, they're going to be a nice, beautiful string of planets in the mornings. May 30th is the new moon, and that's great for our hopefully meteor shower, storm, whatever it's going to be. And it's oftentimes we have when we have a nice meteor shower, there's too much moon, but this is going to be great. So new moon. And in the United States, we're celebrating Memorial Day that day as well. June the 7th is the first quarter moon. June 14th is the full strawberry moon. On June 16th, Mercury is at its greatest western elongation. That's the highest it's going to be, again, in the morning before the sun comes up. June 18th, Saturn and the moon are in conjunction. On the 19th, Father's Day and Juneteenth. Does anybody else in the world celebrate Father's Day or Juneteenth, or is that just a United States thing?
Juneteenth, this will be the second year that it's a holiday.
I've heard it's been around for a very long time.
It's been around, but it'll be an official holiday.
Yeah, right, right.
I wouldn't call it celebrate Father's Day, but we it exists here in Canada.
It's kind of a big deal here. Not quite as big as Mother's Day, but anyway, on June 20th is the last quarter moon. The 21st, Jupiter and the moon are in conjunction. It's also the solstice. June 22nd, Mars and the moon are in conjunction. June 26th, Venus and the moon are in conjunction. And then we're back to a new moon on June the 28th. So that covers about a month.
Early June, what's going to be cool is all the planets in the dawn sky will be in naked eye planets will be in order: Mercury, Venus, Mars,
Yeah,
Jupiter,
pretty much.
Saturn.
You'll pretty
Yeah,
much
once
see.
They just need Mercury to get in line, and Mars and Jupiter switch places, and that'll be kind of neat to see them.
That's
Yeah,
cool.
A lot of the
naked eye order.
mornings.
Yeah.
A lot of the mornings. I mean, a lot of these.
That's really neat.
Pretty much.
Yeah.
Awesome.
You know, dot to dot for the plane of the ecliptic. I think it's really cool.
Yeah.
Yeah, that's really neat. All right. Well, thank you, Pam. Nick, let's talk about NASA's plans to go to the moon and Mars.
Yeah, so this is part of NASA's Human Exploration Program, where the specific overarching umbrella is the Moon to Mars program. And it's talking about returning to the moon, which is the Artemis program, but it's using that to prepare for longer journeys into deeper space, which is ultimately sending humans to Mars. The timeline NASA is talking about for Artemis is sending people sometime this decade. For Mars, they're talking about next decade or maybe early 2040. So, if you're in your 20s now, hopefully, of course, they said that to me when I was in my 20s.
Yeah.
Anyway, so they're doing something a little bit unusual right now, which is they're actually looking for public comment on 50 different objectives that they have for this whole Moon to Mars program. So this is both what we're trying to do in going to the moon, and this is not just like the Artemis program. This is even going beyond that. What do we hope commercial partners will pick up on? What role do we see NASA playing in this? And what should we be aiming towards? The whole idea is trying to outline what are we trying to get to? Where do we want to go with this? And then breaking that apart into, all right, how do we do that? What are the individual pieces of that? Then looking at, okay, what's currently going on and what's missing from that? So this is NASA trying to go from a what can we do perspective, where it's the what do we have sitting around, what can we do with it, to a where do we want to go long-term perspective. So they published these 50 objectives along with a very nice a glossary to go over what are these terms we're using, like what does it mean if NASA is trying to develop a technology versus demonstrate a technology. Development is the whole bore. NASA wants to really do it. Demonstrate is we just want to prove it can be done. Like we're just going to do it once and then let someone else develop that further. So it's really trying to get the public on board with what is it we're thinking about and getting comments back. There's also half an hour or a little bit longer than that video that they published to help explain what they're talking about, what's the context for all of this, and what sorts of comments are they looking for. And to add a little incentive to this, NASA has actually said that if your comments are particularly interesting, they may contact you to come and be part of one of the 2 in-person seminars that they'll be putting together to really talk about these and flesh them out in more detail and really help determine what NASA is going to be doing for the next while in terms of human exploration, return to the moon, and beyond onto Mars.
It's funny. I looked through the list a couple of days ago when they published it, and they all just make you drool, and they're all like encapsulating just these incredible, grand, sweeping ideas in a single sentence about
What was really
harvesting.
funny for me.
Oh
yeah, a lot of these, like some of them are stuff that we've been bandying about for a while and start to feel realistic.
Yeah.
But other ones that I look at, I'm like, that's straight up science fiction. That's awesome that we're actually talking about, okay, how do we do it?
Yeah.
So it's actually really cool. They split into 4 major categories, which is the different colors you can see on the slide that Pamela is projecting for us. There's transport and habitation, there's infrastructure, there's operations, and there's science. And all of this is trying to help NASA outline what exactly is it that we're aiming for and what pieces do we need to get there.
Yeah. Yeah. And so, like, give us some examples of stuff that were kind of mind-blowing in this list for you.
Well, one of the ones that really stood out to me, just in terms of like, this feels like sci-fi, not like reality, was one of the objectives in operations and infrastructure rather, was how do we develop a concept for a lunar global power grid? Now, this isn't NASA saying we're going to build a power grid that covers the whole moon. It's what would it look like if we did? What's the design principle here? And how do we do that? And this to me was just flooring nuts because We don't have anything even like that on the Earth.
Right.
Like the US is split into 3 grids, the Eastern grid, the Western grid, and Texas.
The Texas grid.
No comment on that. But, it's the idea of coordinating, power transmission over very long distances from disparate sources. I mean, one of the unique challenges to the moon is if you want to use solar power, which is a wonderful gimme, you're only going to get that consistently at either pole. But you really want to live on the equator. So how does that work?
Right.
So this is NASA saying, okay, seriously, if we want to live there, what do we need in terms of basic infrastructure, and what are some of the ideas out there for that?
Yeah, how do you get
So if you're
through
a professional
the 28-day cycle of 14
this
days
is one
of
of the
day
big
and
problems
14
with
days of night?
this is one of the huge problems with landing anything on the moon. So there are actually a whole slate of missions going to the moon for small-scale science missions that specifically are only for a lunar day. 2 weeks.
Yeah.
You get 2 weeks for that rover, because there's no way we want to design that darn thing to last through the night. Because, freezing temperatures and pitch black with no power source, that's brutal on electronics.
Snooks.
So what kind of time frame do you think this is encapsulating?
I'm not really clear on that. But I think that's part of what's interesting about it is this is supposed to be getting us all the way through human setting boots on Mars. That NASA is saying is going to be 2040. Every timeline I've ever seen for anything involving space slips to the right. But, that's kind of looking at the next 20 years of what will humans do in space, at least from the government-led program perspective. So this is the beginning seeds of something like the Decadal Survey that runs all of what's going on with planetary science and heliophysics and all the rest of what NASA does with robots and telescopes.
Yeah.
This is human space exploration saying, what are we going to do? What are our marching orders? How does that look? So as you can tell, I'm a little excited about it.
Yeah. I mean, it's funny. I mean, it just and I think you hit the nail right on the head that some of this stuff just seems like perfectly reasonable, sorting out in space refueling and storage and so on. And then some of them are bonkers, like a global energy system for the moon, in situ resource utilization on Mars, return trajectories. There's all kinds of crazy stuff in there. And it's nuts and wonderful. Yeah.
And if you have ideas for it, NASA wants to hear from you.
Yeah.
So seriously, there's an open public forum for you to go write a note to NASA.
The Apollo ALSEP payloads did leave some nuclear RTGs on the surface. They might still now technically they don't have USB ports. It might be too hard to not just plug in to get juice off them, but they're probably still powered up.
It's funny you should mention that, Dave. One of the line items in this is, how do we make use of things that are already there?
Interesting.
So what are some ideas for landed things that are there that, for example, that RTG may still be hot?
Oh, yeah.
It may be defunct because
I think
it's not just, is the power source still going? It's,
how do you
does it
plug
still
into
operate?
it? Yeah, how do the technical...
And that too.
Like I said, there's no USB port to just plug into it.
So what would you need to cannibalize what's there to do something productive?
Interesting.
That's a line item in this.
Yeah.
So
I thought that
really
was a crazy idea.
High.
I guess not.
Yeah.
Nope.
Interesting.
So
this is part I think so cool.
Well, what about a space power satellite? That doesn't have to be a problem in the shadow of the moon if it's in orbit.
Yeah. I actually did an interview with someone talking about space power just a week ago, and it's some really interesting new technological advances. It's probably less interesting to try and send power back down to Earth from space, but it's really interesting to send power from satellite to satellite in space. And in this case, you could send power to you could be out in the sunlight, and then you could send power to something that's in the shadow. And there's a lot of really interesting ideas to be able to do that. So, yeah, very cool. All right, well, let's just give a quick mention that the Boeing CST-100 Starliner that flew to the International Space Station, only 2 of its thrusters broke.
It made it.
It made it. It was able
Yeah.
to dock with the space station, and just a couple of hours before we're recording this, it detached, returned to Earth, was recovered.
They landed at White Sands over like on land too. That was kind of interesting. It wasn't an
it's
ocean
different from
splashdown.
the Crew Dragon. The
Yeah.
Starliner is designed to land on Earth and not land in the water the way Crew Dragon does. So I don't know which landing I would prefer. I've heard the Soyuz landings are pretty hard.
They say it's like a low speed car crash in Soyuz. So
Yeah. Yeah, so we'll see.
That's always how I want to hear my space capsules described. It's like a low-speed car crash.
Yeah,
No,
we'll see. I wonder
thank
if Boeing is going to feel the same. Yeah. All right. We've reached the end of our hour, so I want to give my co-host a chance to shamelessly self-promote what they're working on. Dave, what are you working on?
Frequent contributor, Universe Today, Sky and Telescope, author of first book with Universe Today, my Deep Sky Guide that came out a few years ago, and I will probably my next mission will be out to watch the Tau Herculids Tuesday morning, and if it just is the amazing shower of the century, I'll probably be getting a lot of photographs to do an article about.
Fantastic.
Cool.
And Astro Guys with a Z.
With a Z, yes, because if there's a meteor storm, I will be tweeting like OMG meteor storm. So yeah, keep an eye on my account. All
right, Pam, what are you working on? Where can people find out more?
We are still broadcasting live on Friday nights on the Everyday Spacer YouTube channel, the Everyday Spacer Facebook page, and we got some pretty cool stuff coming up. May 27th, we're going to talk about collecting meteorites. Very timely, that. And June the 3rd, we're actually going to take listener questions, and we'll have people come on and talk to us. And we've got some guests in the hopper. Neil Simmons, Don Dowdy, and Bruce McKenzie are out there. Also, you are invited to share live with us as well. You can be a guest. You can come twice a year to open mic night. And we have the listener questions episodes. It's kind of random, but like I said, June the 3rd, we're going to take your questions, everyone in the audience.
You have gotten terrifyingly smooth at this, Pam.
Okay, well, thank you.
That was good. That was good stuff. All right.
Thank you.
Nick, what are you working on? Where can people find out more?
I don't want to have to follow up on that one.
Yeah.
So I am the Wandering Scientist, which I am very, very slow at right now. But I'm also about to wander as a scientist. I'm in the process of moving to Florida, of all places, starting a new postdoc gig where I'll still be doing geochemistry, and I've carved out a bunch of time to keep doing planetary science. But I'm also going to be looking at remediation of coal ash, so saving the environment, not just on Mars.
Nice.
What's coal ash?
And if people want to follow your stuff, where do they go?
At Wandering Scientist.
Perfect.
Which I promise to post to eventually.
Don't promise. It's fine. It's fine. Twitter's in a state of flux right now. Nick, you probably haven't heard this, but it's, don't worry about it.
Yeah.
All right. Well, of course, I'm Universe Today on all the things. We've got a really cool interview coming up on Friday morning. With an evolutionary biologist, and we're going to be talking about the jump from single stage to multi-stage. Dr. William Ratcliffe. We're talking about the jump from single stage to multi-stage organisms, which is totally out of my wheelhouse, but I'm really excited to talk to him about this and the implications for astrobiology.
Single cell to multi-cell.
Single cell to multi-cell?
Yeah, they're not rockets.
Not rockets, yeah. Single stage, right. Did I say single stage?
Yep.
Yeah.
Little details.
Space on the brain. Single cell. That's awesome.
I wonder why.
All right. Cool. Anyway, that's going to be on Friday morning. So thank you, everyone, for joining us this week. Thanks to our special guests. Thanks to all of my co-hosts. Thanks to everyone watching us both on YouTube and on Twitch. Thanks to our special guest. Thanks to Pamela for engineering behind the scenes. She was with us all along, right here. And we will see all of you next week. Thanks, everyone. And thanks, Nancy Graziano, for organizing this.
Yes.
Take care, everybody.
Thanks, everyone.
Good night.